Gents, shall we have a look at these together? X to the power 5 times x to the power of minus 3. I got on the top of mine. Where's that gone? Oh, perhaps I... Oh, okay. That's right. No worries. This one. So multiply these brackets. What you got? 3x squared minus 7x. I agree in entirety with that. Anybody else got anything different? No problem at all. Right, factorise 5x cubed minus 25x squared. X bracket 5x squared yeah. Sorry? Yeah. You can do 5 bracket, yeah. That is also correct. Daniel, you've got to say something else?
X bracket.
Where's the 5 gone?
5.
No, because you won't be dividing the x that you've took outside by 5. Yeah. So you can't do that one. If you're going to divide the whole function by 5, yeah, you can. Yeah, but that ain't something you do. The succinct answer. Anyone else got anything different? 5x squared brackets minus 5 yes, they are. That is the absolute simplest form. You've taken out as much as you can. But just tried to say to you this morning, we're doing this in isolation at the moment. When you're going to solve a problem, you're going to be looking to try and get better on it, like the last one. Yeah, so we trying to do that would make it together as one on one side, and then, so we're not on this particular reason at the moment. It's less clear as to what the answer is. Okay, but all these examples, apart from one that had dividing by 5 in it, were kind of a right way. Yeah. What about this one? Solve 3x plus 2 equals 14. X does equal 4. The process is that we can take 2 from both sides and say 3x is equal to 12. And then we divide both sides by 3 to end up with x is equal to 12 over 3. Yeah. So, in a way, you have to be a little bit careful, but in a way you can think of that rearranging thing as you do it in the opposite of bid mass. You cannot divide by 3 until you've got the 2 over on the other side. Because if you divide this side by 3 straight away, you'll lose the 3 in front of the x, but you'll turn that bit into 2/3. Yeah? Okay? That's that one. Solve 7x minus 2 is equal to 3 plus 14. What's the answer we got? X is 19 over 7. And this is where I said don't be frightened of leaving something as a fraction. So we effectively add 2 to both sides. We end up with 7x is equal to 19, and then divide both sides by 7. So x is equal to 19 over 7. Yeah? And lastly, make R the subject of A is equal to pi r squared. Formula for the area of a circle. What's the first thing we can do? Divide both sides by pi. We get A over pi is equal to r squared.
Square root r squared.
Who's got pi over A? And then square root both sides. So we can say r square root and gets rid of the square is equal to the square root of A over pi. Yeah. No, the thing is, if you do the square root first, let's just write this out here. A is equal to pi r squared. Yeah. If you do square root of both sides first, yeah, what you're effectively ending up is root A is equal to the root of pi times r. Have you got any further towards your problem? So the issue is you could in some cases get there in the end, but it's going to be a much longer thing, and you'll only get used to this with practice. Keep practicing and you'll learn to see the best way to go about things. So the way to tackle it in this case, we want r on its own. Yeah, so get rid of that first. So let's divide by the pi. Float. So 1 but squared. So to get rid of the square, take sides. Alright? Yeah. With practice that you know what to do. Yeah? The reason you might want to factorise is if you've got an expression with two x and you want them together. You can draw them outside the brackets and then shift all the bracketed terms together. Yeah? Alright? And we will come to some examples like that. Because that's a preamble. Remember, I thought we'd look at this. Alright? So, laws of indices, solving simple equations, rearranging formulae and equations, solving indicial equations using the laws of logarithms. So, laws of indices. I've got to go back to my notes from a smaller note. Laws of indices. First of all, we've got a number with an index, x to the a, base, power. They're the mathematical names, or index we call that. Yeah. The first in multiplication, where it says x to the times x to the as to x to the a plus. So in the example, broad is equal to 9. Yeah. Second law. So when we multiply two numbers together that have got the same base, in this case x, we can simplify by just adding the two powers together. Second law for division. If we've got a to the a, x to the a over x to the b, the result is x to the a minus b. So in the case of x to the 7 over x to the 4, the result is x to the 3. Yeah. So when one number is divided by another, simplify by subtracting the denominator index from the numerator index. Again, with division, you must get it the right way round. You must subtract the bottom one from the top one. With multiplication, order doesn't matter. Third law of indices. If you have a number x to a second power b, the result is x to the a times b. So in this example, we've got x squared raised to the power of minus 3. That's equal to the x to the, I'm going to write that out in full this time, x to the 2 times minus 3, which is x to the apply together a positive number and a negative result. Two similar signs, positive result. So when we got a number raised to a power, all raised to a second power, we simplify by multiplying the fourth law, not the second as it is on my copy and paste notes, I would think. Copy and paste. If we have x to the a over b, that's equivalent to the bth root of x to the a. Right? So x to the 5 over 2 is equal to the square root of x to the 5. So the denominator that is the root, and that's the numerator that is the power underneath. Okay? Yeah, you can put the 2, but normally we don't put the 2 for a square root. That's just by convention. For square root we just do that. It's the square root of x. That is the cubed root of x.
Oh, yeah.
Yeah, which would be, that one is x to the power of a third. Yeah? And you're going to need to be able to take terms that have got root signs and turn them into numbers with indices when you do calculus. Because we'll not be able to do calculus in that form. We need it in indices form. So you need to be able to go backwards and forwards between the two. Alright? If you remember that the square root is x to the half, then you can remember that it's the bottom number that gives you the denomination of the root, and that's the top number that gives you the power of the x inside. Alright? So, what would this one be? Yep, x to the 8 over 6. Sorry? We you could write it as x to the 2.5, but it's more normal to keep it as a fraction. If you're talking about this one, are you? Yeah, it's more normal to leave it as a fraction. I mean, we can simplify this 8 over 6, can't we? To 4 over 3. Yeah? Alright? But other than that, that wouldn't be a right, it's not a wrong answer, none of it, as long as they got that correct to that, those two are equal. If you're unsure, give x a value, put both versions in your calculator, you should get the same answer. So just say, do they both work if x is 5? And they should give you the same answer with x is equal to 5 or 10 or whatever. Alright? Reciprocals. X to the minus a can be written as x to the 1 over plus a. So effectively, we can write, when we get a reciprocal like this, 1 over x to the a, we can bring the x to the top of the fraction, but we have to change the sign of the index. Yeah. Now that is useful also in calculus. We wouldn't be able to differentiate, for instance, 1 over x to the 5, but we can differentiate x to the minus 5. X to the minus 4 can be written as 1 over x to the plus 4. Reciprocal means turn the fraction up the other way. Alright? A couple of other important ones, okay, are power of 1. X to the power 1 is equal to x. That means any number can be written as that number to the power of 1, if that's useful to you. That is still the same number. Okay? So a to the 1 is a. Yeah. Sixth law, power of O. And again, a really useful way in some things of being able to express the number 1. Any number to the power 0 is 1. So any number we can write as being 0. We can write 0 as being x to the power of none. Yeah. And that will again later on become useful in helping us to understand why some of the things work the way they do in mathematics. Being able to write the number 0 as any number to the power 0. The number 1 as any number to the power 0, sorry. Alright? Are we all reasonably happy with that? And you're going to make extensive use of that in various different topics as we go through the module. So I'm not going to labour on it too much at this moment in time. There's, in your notes, I have to get this board fixed, there are lots of examples that you can have a go at your leisure. If you've got the book yourselves, there's probably even more examples you can have a look at in there as practice in sorting out these indices. Perhaps if there's, the idea here is if there's time towards the end of the session, you go back and have a look at the bits and the examples you didn't have time to do, and I'm here to help with that. Alright? So, looking at this one then, solve 6x plus 1 is equal to 2x plus 9. How are we going to, with what we've talked about so far, how are we going to tackle that one? Let me see if I can make that bit bigger. 6x plus 1 equals 2x plus 9. Okay, let's. So what we're going to subtract? So we end up with, on this left-hand side, 4x plus 1 is equal to 9. Yeah? And then subtract 1. And then formally two. Okay. Equally, you could have subtracted the 1 first and then moved the 2x. In that case, there was more than one order you could have gone in and got to the same answer. Yeah? Solve 3 brackets x minus 2 is equal to 9. What we've got to do first? So 3x minus 6 equals 9. So that's brackets. Just make a little note of how we've done it. Brackets. And then what? Add 6 to both sides. So you get 3x is equal to 15. X is equal to 15 over 3. X equals 5. Yeah. Anyone see a slightly different way about going about that one? Yeah, you can start off. You could start off by dividing by 3. We'd end up with x minus 2. So start, divide by 3. X minus 2 that side. Now the 3 is gone from outside the brackets can disappear. Is equal to 3. And then add 2 each side. So x is equal to 5. And in notational terms, if you're writing down every operation, that one's slightly quicker. But if you were given that easier question in the exam, which I'm going to show you won't be, then either of those two answers would get equal marks. Alright? You are expected to show your working, by the way. I mean, ultimately, in a question like that, if your answer says 5, you're going to get the mark. But if that answer isn't right, you can't be given marks for the bits you got right earlier in your working out if you don't post them on the paper. Right, 3 divided by x is equal to 4 divided by 5. How do we go about solving that one? Turn that into 1.25. Not sure how you the right answer in the end. Be the easiest way to it. We want x on its own, don't we? if you multiply both sides by x, we'll write it out in full. You've got 3x divided by x, so we multiplied that side by x. If we do that, to keep this side happy, we've got to multiply that side by x. Okay, now over here, we can cancel those two out. Yeah, so that's fine. We're left with 3 is equal to 4x over 5. Next thing. So that was multiplied by x. Fifth. So that's the same as 4x times 5. I mean, I could, but it'd still be the same. Yeah, okay. Next job, we got to get rid of the 5 and the 4. 5. So we 15 is equal to, and we'll write it separately, 5 times 4x over 5. Those two. Just minus 15. Got to divide by 4, haven't we? Because that's just 4x, you know. Yeah, 4 times x. Is equal to x. Sorry? Yeah. Right, everyone happy? Yeah? Right. Much more common, tricky one to take a look at. And we've got fractions added together here and fractions subtracted. So I'm going to take you through this one, I think, because that's a little bit more tricky. Right? Lowest common denominator of those fractions there. What's the denominator of the number 5, by the way? 1, yeah. What's the lowest common denominator of 1, 2, 3, 4? Those 4. Now, lowest number that all of them will divide evenly into. That's what you're looking for. 20 into 2 will give you, you're going the wrong way. 20 is, isn't it? Yeah? Agreed? Yeah? So what I want to try and do is write all these fractions with 20 underneath. Yeah, so that first one, you've got to multiply the bottom by 4. Have I not? So you've got to do the same with the top. 8y over 20. Yeah. I want 3/4 to be over 20. So I've had to multiply 4 by 5. So I've got to multiply the top by 5. 15 over 20. This is 5 over 1. So 1 over 20. That'll be 100, isn't it? We've already got 1 over 20 there. Minus. And we want this one to be 20. 30y over 20. Because you can write a whole integer as that integer over 1. So to turn that into 20, I've got to multiply by 20. Multiply 5 by 20 gives you 100. Whatever I do to the bottom, multiply the bottom by the denominator by 20, I've got to multiply the numerator by 20 as well, and then I've effectively still got the same number. Right, is there anything I can do, you can see immediately, to simplify that? Yeah, I could do, but it can't do anything. And there's an equal sign in here. Yeah. $15 20ths and 100 20ths, yeah? So we could go 8y over 20 is equal to 115, not equal to, plus 115 20ths is equal to 1 over 20 minus 30y. Okay, now, you could do that, right? But what I'd recommend is, because this is minus 30y over 20 on this side, add that to the other side, and take these two over here. Because then you're you're going to end up with a negative so many y. Yep. So if we add 30y over 20 to this side, now what can happen is these two can join together, can't they? Yeah. So that becomes 38y over 20 plus 115 over 20 equals 1 over 20. And now we can subtract this one from both sides, so we end up with 38y over 20 is equal to 1. Or we might as well write it as minus 114 over 20. Everyone see where that come from? 120 minus 115 twentieths must be minus 114 twentieths. Now can we simplify those two fractions? If you divide that by 20 you end up with 1, but if you divide that by 20 you end up with a decimal. So divide by 2, we end up with 19 over 10 y is equal to, and these are both divided by 2, won't they? 57 over 10. Yeah. Sorry? Yeah. No, you'll end up with y on both sides then. Sorry? Okay, you go on like this. Yeah. How do you get 19 minus 57? No. Multiply by 10 both sides, divide by 19 both sides. And then cancel out and leave 1 sound. Minus 570 over 190. What will that come out as? I'm doing all in one go, multiplying both sides by 10 to cancel the 10 out at the bottom of there. Yep. And then multiplying both sides by, dividing both sides by 19. And all in one go. Do it separately if you like. Let me do it separately. Yeah? Look. you'd be happy with it if that was A and B there. You'd go say multiply by A and divide by B. What's the difference if it's a number? Yeah. So what we're saying is we're going to multiply both sides by 10. Yeah. Where they? Hang on. Where they get that? Oh, I know. Minus 570 over 10. Yeah, and then divide both sides by 19. So divide this side by 19. I end up with y on its own. Yeah, divide this by 19. Y is equal to minus 570. In the most succinct way to go about it, but there we go. What is minus 570 divided by 190? Minus 3. It's a tricky one, but if you think and go about it step by step, follow the rules. No. Right. What I do want to what you to be aware of is if you had some of want to find y. That can be written for 1. That by 2 are cubed. Effectively, saying I'm going to take the reciprocal of both sides. If I turn that one upside down, I can turn this one upside down. And y. If the variable you is on the bottom of a fraction, step 2 the reciprocal of both sides. Take the reciprocal of all sides. Fine. Little trick perhaps to make. Alright? And have you all got everything done that you might want? Yeah? Right. Transpose never here and student at all levels. Transpose a formula. I don't like it. But really, it's no different to the simplifying and solving we've been doing. Formula for the volume of a cylinder, V, pi r squared times L. Volume V is the subject of this formula. The formula will give you the volume V, in terms of the radius r and the length L. If we know the volume and the radius, but want to find the length, we need to rearrange the formula to make L the subject. Okay, so that's what we're going to look at with some examples now. First of all, the key to this is knowing mathematical operations that are opposites of each other, that allow you to move things from one side of the equation to the other. Addition is the opposite of subtraction. So if you're looking at how is that number or letter attached to this side of the equation, I've got to do the opposite operation to move it over to the other side. So if it's attached by addition, we subtract. The multiplication is opposite to divide. It's a two-way thing. Square and square root. Anyone know any others? Yep. On your calculator, inverses are usually the function key on many of the other functions. Alright, what about e to the x? No, have a look on your calculator. What's the shift? What's the shift function on the e to the x button? Or what button goes with e to the x? E to the x might be shift. ln, is it not? Natural log. They're opposites of each other. Yeah? What's the inverse of log x? Ten to the power of x. Yeah. Sine x. Sine minus 1 of x. And the same with the cosine tangent functions. Okay. When you come to do the two calculus topics, you will very quickly learn that differentiation and integration are opposite mathematical functions. If you differentiate a function, you get a differential, and then integrate the answer, you get back to where you started. Okay? So they are the key mathematical opposites that you'll be using or needing to use to manipulate equations and do algebra. Again, cannot get enough practice at these. So this formula for volume, how are we going to go about turning that into a formula for the length if we know the volume? We could divide by pi first. Divide by pi. What would that leave me with? V over pi. Yeah. You can't do that. If you've got to do it to the whole side, remember. So we're not looking for R anyway. We're looking for L, remember, on its own. So the next operation is, how do we get rid of the R squared? Divide by R squared. That leaves us with V over pi R squared is equal to L. And then just more formally, you can normally put the quantity you're looking for on the left hand side. Right? Yeah, there's nothing wrong with that once you get used to it. If you're a little iffy with this at this point, do it one step at a time until you get really used to it. Okay? All happy with that one, yeah? Right, this one of Newton's equations of motion, V is equal to U plus AT, making U the subject of this. What are we going to do first? Sorry? Subtract AT, yeah. So we end up with V minus AT is equal to U. That was an easy one, wasn't it? Yeah, I mean, it's more proper mathematically to write it that way round, yes. If you wrote it that way around in the exam, you're going to get all the marks. It's correct. Yeah. I'm more pedantic about people making sure they include the units when you've got engineering quantities involved than I am about whether that's in the right order. Okay. What we got here? In a right angle triangle having sides x and y and then a hypotenuse z, Pythagoras' theorem states that z squared is equal to x squared plus y squared. That's the problem. Yeah. Transpose the formula, find minus y squared, so we got z squared minus y squared is equal to x squared. Yeah, then we want to get rid of that, so we'll have x is equal to the square root of z squared minus y. So, to get rid of the square there, we need to do a square root. This side will get upset if you don't do the same. So Nah, don't cancel them out. Alright? If you in terms of the problem, Nat, did that, what you're saying is you're going to say x is equal to z minus y. You're saying for any right angle triangle, one side is equal to the hypotenuse minus the other side. It's not always the case, is it? Right? Right. P is equal to squared x plus a squared y all over r. Make A the subject. Why are you choosing that first, Kieran? Yeah, to get rid of the quotient or fraction. Yeah, so multiply by r. We can do that quite simply. We're going to have P times r is equal to a squared x a plus a squared y. Everybody follow that. Next bit. Not while they're attached to a squared, you can't. No. We've got two things involving A and we only want one. Minus the what? So if I'm just going to do that now. You want me to take? Yeah, yeah, but you'd have. So if I take a squared x away, you have PR minus a squared x is equal to a squared y. You've still got two a's, and now they're on different sides of the equation. There's I can see where you're going, but there's a far easier way than that, where you can get just one a squared in there. Factorise it. Yes, yes, yes. Factorise a squared, so we can say PR is equal to a squared is in both those two terms, there and there. So we can write that outside some brackets and multiply it by x plus y inside the brackets. Yep. So now we've only got one term with a in it. Still squared, and it's still multiplied by x times plus y. But we got rid of this 2a squared problem. Two lots of a squared. So what can we do now? Divide by x plus y. We can do that all in one go because they are bracketed terms, and we can take the whole bracket in one go. So we can say p over r divided by x plus y. Now, you don't have to put brackets on that. That's implied by the line. But if you want to, if you remember it better by doing that, then please do. Okay. and that's to a squared. And now you have to square root it. You like your square roots, don't you? Square root of both sides, we end up with a is equal to the square root of, and of all that side, p times r over x plus 1. Sometimes worth putting a little dot in there for high level multiplication between them, so you know that's two variables and not the variable PR. Alright. P times R. Alright? So that's one where we need to have that knowledge of being able to factorise. Take out a common factor. Right, how are we doing for time? We got till 3, haven't we? You get be fed up with me by the end of the day. The indicial equation. If, as in the example, an equation involves the power index, where x, the unknown, is either the base or the index, we have an indicial equation. We can solve an indicial equation by using logarithms, usually to the base of 10. Alright, so that sounds like a mouthful, doesn't it? So should we have a go at it and see how we do it? Yeah. So we'll look at what we're saying here is we've got 10 to the power of x is equal to 36. We want to find out what x is, what the power is. Yeah. So, logarithm to the base 10 of the number is the power to which you have to raise 10 to get that number. Alright? So the log on your calculator, the log button on your calculator, finds the log to the base 10 of a number. So, using your calculator now, find the log to the base 10 of 1,000. If you use the log button, that is automatically assumed to be base 10.
If I put log 10, it gives me 1.
You've got to do log 1,000.
Oh, okay.
Yeah. If you want, there is a button on my calculator for logs to different bases. But we will only be doing either base 10 or natural logs to the base E anyway. So you've got to push the log button. 1,000 equals. You should get 3. 10 to the power 3. 10 raised to the power 3. 1,000. So do you see the log of the index that you'd have to raise 10 to get the number. What's the log to the 98? 1.991. Now if you do 10 to the power of 1.991, yeah, 97.954, and that's simply because you've rounded that value. Okay, so log and 10 to the power of x, log x, are opposites of each other. We talked about that earlier. Right, laws of logarithms. Remembering that a logarithm is a power, usually with 10, so the laws of indices apply, but they are written as the laws of logarithms. So we can write that the log of two numbers multiplied by each other so the log of A times B is equal to the log of A plus the log of B. Sometimes these different ways of writing things can be useful in moving an equation around. So if we ended up with an equation where we got two logs added together, that was useful to us in rearranging that, we could write log A plus log B as log A times B. Or if we end up with something that looks like this one, we can write it as log A plus log B if that's what we need. The log of A divided by B is equal to the log of A minus the log B. You've got to be careful with order there. It's the log of the numerator, take away the log of the denominator. Alright, back when I was at school, no calculators. You might have a slide rule if you were lucky, but a way to multiply was the log of the big numbers, both of them, from the log tables book. Add the two logs together and find the anti-log of the result, and then multiply the two numbers together, and that's using that rule. Yep. You don't have to do it now, do you? You push buttons on the calculator. Right, but in you'll kind of come across equations with powers in that you need to express as logs or vice versa. Yeah. Log of A to the n, so log of a number to another power is equal to n times the log of A. Again, that can be useful. I know there's somewhere within the module we'll be using that different way of writing to be able to manipulate an equation. I can't remember off the top of my head where it is now. And the log of 1 is 0. Remember, 10 to the 0 is equal to x to the 0 is equal to 1. Alright, so the log of 1 equals 0. They're all useful ways of being able to write. Remember, we can write the number 1 to the 0. Alright. Laws of logarithms can be applied to solve integral equations. Solve the equation 2x to the power 3 for significant figures. Two to is equal to 3. Find x to 3, 4 big fig. The way we do this, take log base 10 both sides. So for log base 10 just log without 10. Alright? What we do as we go log of 2 to the x is equal to log of 3. And they're all to the base 10. Now, looking in your laws of logarithms on the previous page, can you see something on there that we can write in a different way? Explain yourself. Third one down. You know, we can write this side.
Yeah.
Because it says you can write log a to the n. So we got log 2 to the x as log n as n times log a. So we can take x out times the log of 2. That's using that third law, just write it in a completely different way. And that's still equal to log of 3. No, you can't do that. But what can we do now? Remember, this is multiply in there. Yeah, so what we're doing is dividing by log 2. Yeah, that logarithm is multiply, isn't it? That's x times log 2. So if we divide by log of 2, we end up with x on that side now we can put that in the calculator, can't we? Put x on its own. .585 to 4 significant figures. Is that one any significantly different? Let's just have a look at this one, because that one's fairly similar to the one we just did. 4x plus 2 equal to 13.8. Is that the best way to start? Remember, we want that term there on its own, away from being part of that law. The law again, yeah, we can put x plus 2 log of 4. By that third law, we can write that like that. Is equal to still 13.8 at the moment, because all we've done is we haven't changed that side, multiplied it by anything, we've just written it in a different way. Is there another law that will allow us to do something slightly different to that? I think you can do what you're saying. That ain't what I've got down here. Let's just try that. You're saying x, that's different to what I got down here, and I don't know why, because you're saying divide through by log of 4. So we'd have x plus 2 that side, and 13.8 over log 4 there. Yeah? And then x is equal to 13.8 a log of 4 minus 2. We haven't done no log of both sides. X is equal to what? From that. Oh. What's all? He's written that bit as x log 2. Hang on. Keep looking at the wrong one. X log 4 plus 2 log 4 plus 2 log 4. This is, let me show you what's been done. He's multiplied out those brackets, so he's gone x log 4 plus 2 log 4 is equal to 13.8. And then, that's what he's done. Sorry, taken the log side, hasn't he? Yes. I'll tell you what I'm going to do, guys, is I'm going to check that out. And we'll sort that out next week, okay? Because there's something strange not understanding about that, because I can't see anything wrong with the first we've been about I'm dividing through by x plus 2 to make it 13 over. Sorry, dividing through by log 4 to make it 13.8 over log 4. I couldn't see nothing wrong with that. So I'm going to check that one out, and then we'll make sure we got that right next week. Okay, here's the answer.